Ask most people what's happening with the ozone layer, and you'll usually get one of two answers. Either it's an old 1980s problem that got fixed decades ago and stopped mattering, or it's still a live crisis, a gaping hole sitting over Antarctica getting worse every year. Neither answer is quite right, and the actual truth sits somewhere more interesting and more instructive than either of those two extremes. The ozone layer is genuinely healing. That part is real, well documented, and represents one of the most successful pieces of international environmental cooperation in modern history. But healing isn't the same thing as healed. The timeline for full recovery stretches out decades into the future. And over just the past year, researchers have identified a new, previously overlooked threat that could meaningfully slow that recovery down if it isn't addressed. This is the actual current state of the ozone layer, not the simplified version from either side of that old debate. Before getting into the current state of things, it's worth being precise about what's actually being protected here, since the phrase ozone layer gets used pretty loosely in casual conversation. Ozone is a molecule made of 3 oxygen atoms bonded together, distinct from the 2-atom oxygen molecules that make up the air we actually breathe. In the stratosphere, roughly 9 to 22 miles above Earth's surface, ozone in this layer functions essentially as a planetary sunscreen, filtering out the specific wavelengths of UV radiation that are most damaging to living tissue, DNA in particular, before that radiation has the chance to reach the surface and cause harm. Without that filtering effect, the amount of harmful UV radiation reaching Earth's surface would increase substantially, with direct, well-documented consequences for human health, including sharply elevated rates of skin cancer and cataracts, along with broader damage to crop yields, marine ecosystems, and the phytoplankton populations that form the base of the ocean food chain and play a meaningful role in the planet's carbon cycle. The ozone layer isn't a nice-to-have atmospheric feature. It's a load-bearing part of what makes the surface of this planet survivable for complex life the way it currently exists. The specific crisis that made ozone layer a household phrase in the 1980s traces back to a class of human-made chemicals called chlorofluorocarbons, commonly known as CFCs, which were, for most of the 20th century, considered something close to a miracle of industrial chemistry. They're stable, non-flammable, non-toxic to handle directly, and extremely effective as refrigerants, aerosol propellants, and foam-blowing agents, which is why they ended up used extensively in refrigeration, air conditioning, aerosol spray cans, and industrial foam production for decades. The problem, undetected for years after CFCs entered widespread use, is what happens to these molecules once they eventually drift up into the stratosphere. CFCs are stable enough to survive the journey largely intact, but once exposed to the intense UV radiation present at that altitude, they break apart and release free chlorine atoms. Those chlorine atoms then go on to catalytically destroy ozone molecules. And critically, each individual chlorine atom doesn't just destroy one ozone molecule and stop. It can go on to break apart tens of thousands of additional ozone molecules before it's eventually removed from the stratosphere through other atmospheric chemical processes, making even relatively small quantities of released CFCs disproportionately destructive to the ozone layer as a whole. Scientists Mario Molina and Sherwood Rowland first proposed this chlorine-driven ozone destruction mechanism theoretically in 1974, based on laboratory chemistry rather than direct atmospheric observation, a prediction that was met with considerable skepticism from parts of the chemical industry at the time. That theoretical prediction was dramatically confirmed roughly a decade later, in 1985, when researchers with the British Antarctic Survey documented a severe seasonal depletion of ozone concentrations over Antarctica, a depletion considerably more severe than atmospheric models of the time had predicted, revealing what quickly became known as the Antarctic ozone hole. The specific severity of ozone loss over Antarctica, compared to elsewhere on the planet, comes down to the region's unique winter atmospheric conditions, extremely cold stratospheric temperatures that allow high-altitude polar stratospheric clouds to form, providing surfaces on which the chlorine-driven ozone destruction reactions proceed considerably more efficiently than they otherwise would in the open atmosphere elsewhere. What happened next is the part of this story that gets genuinely remarkable, particularly when set against how most large-scale international environmental problems tend to play out. Rather than years of contested science and diplomatic gridlock, the international community moved with unusual speed. The Vienna Convention for the Protection of the Ozone Layer was adopted in 1985, the same year the Antarctic ozone hole was first formally documented. And just 2 years later, in 1987, the Montreal Protocol on substances that deplete the ozone layer was adopted, establishing a binding, internationally agreed schedule for phasing out CFCs and other ozone-depleting substances. The Montreal Protocol has since become, by wide scientific and diplomatic consensus, one of the most successful environmental treaties ever created, and one of the very few international agreements to achieve universal ratification, meaning every single country recognized by the United Nations has formally signed on. Over the decades since its adoption, the treaty has been strengthened through several subsequent amendments as scientific understanding of the problem improved and as safer chemical alternatives became commercially available, and it has driven the phase-out of over 99% of the production and consumption of controlled ozone-depleting substances worldwide, chemicals that were once used extensively across refrigeration, air conditioning, firefighting foam, and a range of other industrial applications. The measurable results of that decades-long sustained international effort are now genuinely visible in the atmospheric data. According to the most recent World Meteorological Organization Ozone Bulletin, published in September 2025, the ozone layer is confirmed to be healing, continuing a recovery trend scientists have been tracking and expecting for years. The 2025 Antarctic ozone hole specifically came in as the fifth smallest observed since 1992, the year the Montreal Protocol's provisions began taking effect, and closed on December 1st, the earliest seasonal closure recorded since 2019. During the peak of the 2025 depletion season, running from early September through mid-October, the average extent of the ozone hole measured approximately 71 million square kilometers, an area meaningfully smaller, on the order of 30% smaller than the largest ozone hole ever recorded back in 2006. It's worth being precise here because the ozone layer is recovering tends to get flattened in casual conversation into the problem is basically solved, and that's a meaningfully inaccurate compression of what's actually happening. Ozone-depleting chemicals, once released, persist in the atmosphere for a genuinely long time, in some cases many decades, before they're fully broken down and removed through natural atmospheric processes. That means even though production of these chemicals has been almost entirely phased out globally, a substantial existing atmospheric burden of previously released CFCs and related compounds is still working its way out of the stratosphere, and will continue doing so for years to come, which is precisely why full recovery was always expected to be a multi-decade process, rather than something that snaps back quickly once new emissions stop. Based on the most recent quadrennial scientific assessment of ozone depletion conducted in 2022, the ozone layer is projected to recover to its 1980 baseline condition, essentially the state it was in before the appearance of the Antarctic ozone hole, at different points depending on the specific region. Recovery over the tropics and mid-latitudes, where ozone depletion has historically been considerably less severe than over the poles, is projected for around 2040. The Arctic, which experiences its own seasonal ozone depletion, though generally less severe than Antarctica's due to differing polar atmospheric conditions, is projected to reach full recovery around 2045. Antarctica itself, where depletion has historically been most severe, isn't projected to reach full 1980 baseline recovery until around 2066, roughly 80 years after the Montreal Protocol was first adopted. A new, updated quadrennial assessment is scheduled for 2026, which will incorporate the latest atmospheric data and modeling to confirm or adjust these specific timelines. That's the honest shape of the truth in this story's title. Genuine, measurable, scientifically confirmed recovery is underway, driven by one of history's most effective pieces of international environmental cooperation, but it's a recovery still measured in additional decades, not something that's already fully behind us, and the specific pace of that recovery remains sensitive to factors that weren't fully anticipated when the Montreal Protocol was first drafted back in the 1980s. This is where the story gets genuinely current, and where I think the most underreported part of the ozone story actually sits. In September 2025, an international research team, including MIT scientists, published findings identifying a previously underappreciated threat to the pace of ozone recovery, one connected to an industry that barely existed in any meaningful commercial form when the Montreal Protocol was first negotiated: commercial spaceflight. The booming space industry, driven by the dramatic growth in both government and private sector rocket launches and satellite deployments over the past decade, has introduced a genuinely new source of ozone-depleting chemical emissions directly into the upper atmosphere, one that operates through a somewhat different mechanism than the CFC emissions the Montreal Protocol was originally designed to address. Rocket launches and the atmospheric burnup of satellites and rocket stages at the end of their operational lives both release chlorine and other reactive chemical compounds directly into the stratosphere and mesosphere, precisely the altitude range where ozone depletion actually occurs, effectively bypassing the slower process by which ground-level CFC emissions have to gradually drift upward over years before reaching the stratosphere and beginning their ozone-destroying reactions. The research team's analysis found that current real-world leakage and emission rates from rocket propulsion systems are running measurably higher than earlier atmospheric models had assumed, and their modeling indicates that if this emerging source of ozone-depleting emissions isn't specifically addressed through updated policy and industry practice, it could delay the ozone layer's overall projected recovery timeline by approximately 7 years beyond the current 2040-2066 window outlined in the 2022 assessment. Given how rapidly the commercial space launch industry has been expanding, and given that most existing international ozone policy frameworks were designed decades before this specific emission source became a meaningful factor, researchers involved in the study have specifically flagged this as a genuinely new policy gap requiring dedicated attention, rather than something that's likely to resolve itself automatically as existing Montreal Protocol provisions continue playing out. There's a second, somewhat different wrinkle to the ozone recovery story worth understanding, one that involves the very chemicals that were originally adopted specifically to replace CFCs. As CFCs were phased out under the Montreal Protocol, industry largely transitioned to a class of replacement chemicals called hydrofluorocarbons, or HFCs, which share many of the useful physical properties that made CFCs commercially valuable, effective refrigerants and foam-blowing agents without containing the specific chlorine and bromine compounds responsible for directly destroying stratospheric ozone. In that specific sense, the transition to HFCs was a genuine success story within the broader Montreal Protocol narrative. HFCs don't meaningfully deplete the ozone layer the way CFCs did. The complication is that HFCs turned out to be extremely potent greenhouse gases in their own right, in some cases, thousands of times more effective at trapping atmospheric heat, molecule for molecule, than carbon dioxide. As HFC use expanded globally to fill the gap left by departing CFCs, their growing contribution to overall greenhouse warming became an increasingly significant concern in its own right, entirely separate from the original ozone depletion problem the Montreal Protocol had been designed to solve. In recognition of that emerging issue, the Kigali Amendment to the Montreal Protocol, adopted in 2016 and now ratified by 164 parties, established a coordinated global schedule for phasing down HFC production and use as well, extending the treaty's original ozone-focused mission to directly address climate change as well. That phase down is currently proceeding according to its agreed schedule, and current projections suggest it could help avoid up to an additional 5 degrees Celsius of global warming by the end of the century, a genuinely significant climate benefit layered on top of the treaty's original ozone protection mission, and a useful illustration of how the Montreal Protocol has continued adapting to address problems that weren't fully anticipated when it was first negotiated back in 1987. Beyond the specific rocket emissions and HFC stories, researchers monitoring the ozone layer's ongoing recovery have flagged several other factors worth watching, each illustrating a similar underlying theme. Full recovery, while genuinely on track, remains sensitive to developments that weren't fully anticipated decades ago when the Montreal Protocol was first designed. Large volcanic eruptions and major wildfire events can both inject substantial quantities of aerosol particles directly into the stratosphere, and research following events like the 2019-2020 Australian wildfires has documented measurable, temporary disruption to stratospheric ozone chemistry as a direct result, a reminder that natural and climate change-amplified disturbances can meaningfully interact with the ozone recovery process, even in the complete absence of any new deliberate chemical emissions. Nitrous oxide, a greenhouse gas released primarily through agricultural fertilizer use and not directly regulated under the Montreal Protocol's original chemical framework, has also been identified by atmospheric researchers as a growing, longer-term concern for ozone chemistry, since nitrous oxide indirectly contributes to ozone-depleting reactions in the stratosphere through a somewhat different chemical pathway than the chlorine-driven mechanism CFCs use. And current global nitrous oxide emissions, driven largely by expanding agricultural activity, continue trending upward rather than down. None of these individual factors are expected to reverse the overall recovery trend the WMO's own data continues to confirm year after year. But taken together, they illustrate a genuinely important point about how this kind of long-term environmental recovery actually works in practice. It's not a simple, linear, problem-solved, timer running down automatically process. It's an ongoing effort that continues requiring active monitoring, continued policy adaptation, and periodic attention to newly emerging complications. Exactly the kind of continued institutional vigilance the Montreal Protocol's built-in structure of regular quadrennial scientific assessments and periodic amendment processes was specifically designed to provide. It's worth understanding how researchers actually track something as diffuse and invisible as ozone concentration in a layer of atmosphere miles above the ground, since the measurement methods themselves are part of why the Montreal Protocol's progress has been trackable with this much confidence over such a long time frame. Ground-based instruments called Dobson spectrophotometers, first developed in the 1920s and still in use in updated form today, measure ozone concentration by analyzing how much UV radiation at specific wavelengths is absorbed as sunlight passes through the atmosphere on its way to the instrument, since ozone absorbs UV radiation at very particular, well-characterized wavelengths that other atmospheric gases don't. A global network of these ground stations, many operated continuously for decades, provides one of the longest-running continuous atmospheric monitoring datasets available for any environmental variable, giving researchers genuinely deep historical context for understanding exactly how ozone concentrations have shifted over time. Satellite-based instruments have supplemented and expanded the ground network considerably since the 1970s, providing much broader, more consistent global coverage than ground stations alone could ever achieve, particularly over remote regions like Antarctica, where maintaining a dense network of ground-based instruments is logistically difficult. Modern satellite instruments can map ozone concentration across the entire globe on a near-daily basis, which is specifically how researchers are able to track something like the exact size, shape, and seasonal opening and closing dates of the Antarctic ozone hole each year with the kind of precision that produces headline figures like fifth smallest since 1992 or closed on December 1st. A combination of long-running ground stations providing deep historical baseline data and comprehensive satellite coverage providing broad, frequent global monitoring is what allows the World Meteorological Organization and NASA to publish the kind of detailed, confident annual assessments that have been tracking the Montreal Protocol's progress for decades now. It's worth pausing on the scale of harm the Montreal Protocol's success has actually avoided, because the abstract phrase, protecting the ozone layer, can undersell just how directly this treaty has affected human health outcomes at a global scale. Research examining the projected health benefits of the Montreal Protocol, focused specifically on the United States, estimated that the treaty's phase-out of ozone-depleting substances is expected to prevent approximately 443 million cases of skin cancer and 63 million cases of cataracts among people born in the United States through the year 2100, benefits stemming directly from the reduced UV radiation exposure that an intact, recovering ozone layer provides, compared to the continued depletion trajectory the planet had been on before international action was taken. Those are just the U.S.-specific figures from one piece of research. The global scale of avoided health harm extending across every country that would otherwise have experienced increased UV exposure under a continued depletion scenario is considerably larger still, even though it's harder to pin down with a single comprehensive global estimate. Beyond direct human health impacts, the ozone layer's protective function extends into ecosystems and agriculture in ways that are easy to overlook. Excessive UV radiation reaching the surface damages plant tissue and can measurably reduce crop yields across a range of staple agricultural species, and it damages marine phytoplankton populations specifically, the microscopic organisms that form the foundational base of ocean food chains, and that also play a meaningful, if still not perfectly quantified, role in the planet's broader carbon cycle through photosynthesis occurring across the vast surface area of the world's oceans. A continued depletion scenario, the trajectory the planet was actually on before the Montreal Protocol intervened, would have meant compounding damage across all of these systems simultaneously, human health, agriculture, and marine ecosystems, layered directly on top of whatever other environmental pressures those systems were separately facing. Given how many other significant international environmental negotiations, most obviously the decades-long and considerably more contentious effort to address global greenhouse gas emissions, have struggled to achieve anything close to the Montreal Protocol's level of coordinated success, it's worth asking directly what made this particular case different, since the answer has real implications for how future environmental challenges might be approached. Part of the answer is structural and economic. Viable, commercially available chemical alternatives to CFCs existed, or could be developed relatively quickly once the phase-out schedule created clear market incentive, meaning industries facing the CFC ban had a genuinely practical path to compliance. Without requiring a fundamental restructuring of the broader economy, the way deep greenhouse gas emission cuts often do, since fossil fuel combustion remains far more deeply embedded across virtually every sector of the global economy than CFC use ever was, refrigeration and aerosol industries could transition to alternative chemicals over a period of years, incurring real but manageable costs without requiring the kind of sweeping transformation of energy, infrastructure, transportation systems, and industrial processes that meaningful climate action generally demands. The relatively concentrated nature of the ozone depletion problem also made it easier to negotiate around than climate change has proven to be. A comparatively small number of chemical manufacturers produced the overwhelming majority of global CFC output, meaning international negotiators were dealing with a manageable number of key industrial stakeholders rather than needing to coordinate across the enormous diffuse range of energy producers, consumers, and downstream industries involved in global greenhouse gas emissions. And critically, the science linking CFCs to ozone depletion, while it faced real skepticism when first proposed in 1974, became difficult to seriously dispute once the Antarctic ozone hole was directly observed and documented in 1985, providing a stark, visually compelling, scientifically unambiguous piece of evidence that helped build and sustain the kind of broad political consensus needed to move a binding international treaty from proposal to ratification in just 2 years. None of this is meant to suggest the Montreal Protocol's success was somehow easy or inevitable. It required genuine, sustained diplomatic effort and a real willingness from governments and industry alike to act decisively on emerging scientific evidence. But understanding exactly why it succeeded, a relatively concentrated industrial source, commercially viable alternative technologies, and a stark, hard-to-dispute piece of direct observational evidence, helps explain why replicating that same model of success has proven so much more difficult for the broader, more diffuse, more economically entangled problem of global climate change, even though both problems share the same fundamental structure of human-caused atmospheric chemistry requiring coordinated international response. Set against the backdrop of a lot of other current environmental and climate stories, many of which involve genuinely alarming, still worsening trends, the ozone layer's recovery stands out as a rare, well-documented example of a global environmental problem that was identified, addressed through coordinated international action, and is now measurably, verifiably improving as a direct result of that action. That's genuinely worth taking seriously as a case study, not as a reason for complacency about other environmental challenges, but as concrete evidence that this kind of large-scale, internationally coordinated environmental response is actually achievable when the underlying science is clear and the political will to act on it exists. At the same time, the newly identified rocket emissions problem and the ongoing HFC phase-down effort both illustrate something equally important. Even a genuinely successful, well-functioning international environmental framework isn't a set-it-and-forget-it solution. The Montreal Protocol has remained effective for nearly 4 decades, specifically because it was designed with built-in mechanisms for continued scientific reassessment and policy adaptation, rather than being treated as a single, fixed agreement locked in place at the moment of its original 1987 signing. The emergence of commercial spaceflight as a meaningful new ozone threat, an industry that essentially didn't exist in its current commercial form when the treaty was first negotiated, is a fairly direct demonstration of why that adaptive structure has mattered, and why it's likely to keep mattering as new industries and new chemical technologies continue to emerge in the decades still remaining before full ozone recovery is eventually achieved. The honest, complete truth about the ozone layer isn't a simple story of crisis or triumph. It's a genuinely successful, still ongoing recovery, built on decades of sustained international cooperation that remains, even now, an active project requiring continued attention rather than a finished chapter safely filed away in the past. If there's a single useful takeaway to carry forward from this specific story, it's probably this. Environmental recovery on this scale was never going to be a light switch, flipped once and finished. It's closer to a long, carefully managed convalescence, decades long by design, requiring not just the original treaty, but a continuous stream of follow-up assessments, amendments, and course corrections as new complications, HFCs in the 2010s, rocket emissions in the 2020s, whatever comes next in the years ahead, continue to surface along the way. The ozone layer isn't fully healed yet, and won't be for decades more. But the fact that it's healing at all, measurably, verifiably, on a timeline scientists have been tracking with real confidence for years, remains one of the clearest demonstrations available that this kind of large-scale environmental repair is actually possible, provided the world is willing to keep showing up for it,